build creature comforts into a tower of steel and glass. From freight hoists to high-speed pressurized elevators. From ice to nice. In Los Angeles, we're constructing a mega building from the ground up. And we'll use it to explore the development of the systems that make the high life comfortable while meeting the people who design them. Now, building a skyscraper, the human environment on Modern Marvels. No invention helped buildings, including our own, climb high.
If we did not have passenger elevators, we don't have the modern multi-story office building because people won't walk more than 2 or 3 floors off the street to easily reach an office.
The Caltrans building will have 19 elevators to shuttle its 2,000 employees to upper floors. Kone Incorporated will soon begin installing them. But in the meantime, Clark Construction is running a temporary man lift to move workers and materials. At the helm, Bobby Jeffers, man lift operator extraordinaire.
Yeah, you see, you guys, this is a man lift operator's life. You're always getting loaded and you're always having your ups and downs. I've been running the man lift for 25 years all over Southern California. I've built hundreds of buildings. I'm the main person that brings everybody up. The job won't run without me. Whoa!
The site uses an operator for a more efficient flow of materials.
Okay. If I take you down, can I get a nice smile out of you guys? Okay, you ready? Okay, hang on. Hang on, baby.
Bobby decides which subcontractor is performing a more crucial function at the time.
We all have to wait our turn.
That's right. You guys going up or down?
Bobby prioritizes the pickups, but no one cares because he's also assumed the role of site stand-up comedian.
Yeah, I haven't eaten in 3 days. I've been on a diet. A liquid diet, beer and wine. Where are you going, Texas.
Bobby's man lift will only operate until the first 2 permanent elevators are running. Like most of the elevators used in high-rises, these are what's known as roped traction elevators.
This is the elevator car. Cables are attached to the car, go up to the top of the shaft, and then over a pulley or shiv, and then back down the shaft to a set of counterweights that balance the car. Attached to the shiv is an electric motor, and when it operates, it turns the shiv or pulley, and then the car goes up or down the shaft.
Okay, we are in the pit. This is the bottom of the elevator.
At the Caltrans site, Ron Caborn with Kone Incorporated is responsible for getting all 19 elevators up and running.
Anything crooked in the rail, the faster the car travels, the more you'll feel it. These cars travel 500 foot a minute. It's not a real fast car. It's not real slow. It's kind of in the middle.
Electric traction elevators are the most prevalent. They're called traction elevators because it's traction between the motor sheave and the cables that lifts and lowers the car.
Okay, we are in elevator 17 machine room. This is on top of the hoistway. This is our hoist motor, which we have the driver under here with the hoist ropes on it. As it spins, it picks the car up and down, counterweight up and down.
The counterweight on this elevator weighs about 12,000 pounds. That's the weight of the car, plus 50% of the car filled to capacity. This helps ease the amount of work required by the hoist motor.
Okay, right now we're roping up our cars using this elevator steel cable. We're starting out with the spools up at the very top, letting in one dead end all the way down, feeding it through our counterweight sheave. Then we're attaching it with our rope, and then they'll pull it all the way back up to the very top where they put a shackle on it and hitch it up to the hitch plate.
The Caltrans job is going pretty smoothly. Then, one of the elevators hits a bump. After successfully roping 8 elevators, the ropes from one have unexpectedly jumped off their sheave. Dangling over an open shaft, the engineers try to sort out the tangled ropes and get them back on the sheave.
Okay. Okay, this is 1.
Yes.
This is 2.
Yes.
Okay. Okay, establish the next one.
Wait. This one I'm shaking. Look where I'm shaking. This one is 1. This one is
Okay, let me spell it out to you. Grab the number 1 right here, put number 2 right here, so I can get 1 and 2 in order here. Because I can't see it.
The engineers worked 2 days to sort out the problem.
It was quite a project to fix it. We did have it all back up and running again. We noticed that the ropes were damaged. So actually, we have started replacing them. We have to put all new ropes in the car.
Besides the hoist motor, the elevator computer, or controller, is also located in the machine room, above the shaft.
This here is our controller. This is the brains of the elevator. It tells it what to do. It monitors what it is doing.
The computer tells the car what floor to go to, when to open the door, and on some elevators, how much weight just stepped onto the elevator. And believe it or not, the door close button is actually connected to the computer. The controller also regulates the speed of the car. One of the biggest fears people have about riding in an elevator is a sudden uncontrolled free fall.
It's simply the misconception or misperception we have of elevators from television programs and movies where the cables are constantly breaking and the car plummets sort of helplessly down to the shaft. That is almost impossible given modern safety devices.
One of those devices is the governor, which monitors the speed of the car.
If the car were to fall and go faster than it's supposed to, it will recognize that and stop the shift from spinning, and it will stop this cable from spinning.
There are also safety brakes under the elevator car, which clamp down on the rails to stop the car in the event of a fall. If all else fails, there's even a cushion in the bottom of the pit.
So we have a hydraulic buffer here. If the elevator were to fall down the hoistway for a short distance, this hydraulic oil buffer will catch the car. This thing compresses. The faster the car comes, the faster it will stop the car.
With all the safety mechanisms, there's really no need to worry about an elevator plummeting down a shaft. But that hasn't always been the case. Elevators used to be slow and sometimes dangerous, yet luxurious. Still, this economically uplifting invention would change the rules of real estate.
Don't take you 8 hours to do a day's work, does it? Some people are professional man lift riders. I mean, you have those on every job, you know. But you can tell the lazy ones can't walk down one floor. Okay, here we go. Down one? Well, when I was your age, I used to climb the ladder barefooted, and the ladder was laced with barbed wire so I wouldn't slip.
After 25 years of ups and downs as a man lift operator, Bobby's retiring in 7 weeks.
I think Bobby's great for morale because you come in all tired and grumpy, and he'll make sure that you smile, say hello to everyone.
Did you say good morning to everybody, Juanito?
Good morning, everybody.
Come in a bad mood, Bobby's right here, picks you up.
Look happy now, smile. Let's go get him.
Although it might seem like Bobby's been running the man lift since the elevator was invented, mechanized freight hoists actually date back to the late 1700s. English textile mills were among the first businesses to climb aboard. Steam engines or water wheels provided the lifting power to move goods and products. The benefits of elevators were clear, but several deaths caused by freight hoist accidents proved elevators weren't yet safe for transporting passengers. Enter American inventor Elisha Graves Otis. In 1852, Otis installed the first hoist with a safety brake in a factory. The following year, Otis demonstrated his new invention to the public at the Crystal Palace Exposition in New York.
He would have the platform lifted up, and Otis would be standing on it, and then someone would cut the hoisting cable, and the car would fall, and then his improved brake would catch and stop the elevator car, and he would be safe.
Spectacular.
Mirrors, chandeliers, and operator, and it was that gracious moving room that carried patrons of the hotel from floor to floor.
But the elevator quickly changed from luxury convenience to economic necessity. The new invention now made taller buildings feasible, altering the economics of real estate forever. Developers soon realized the new elevating device could also elevate office rents.
19th century New York, primary mode of transportation is horses. Because of not only the horses but other activities, there's a lot of dirt, there was a lot of noise, smells, and being above that had an obvious advantage.
With an efficient means of getting people to upper stories, the top floors, which previously had been less desirable, were suddenly the most valuable space.
The first commercial office building to employ an elevator is the Equitable Building in New York City, completed in 1870.
The trip from the ground floor to the 9th floor, the top story, took just under 2 minutes.
The business community was highly skeptical because this was a slow and gracious device placed into the fast-paced world of American business. There was a recognition that the elevator had to change if it was going to be successful. And it doesn't take too long before the seats begin to disappear and the elevator starts to move much faster.
Over the next 60 years, not only did elevators become faster, but safer and more reliable. Electric traction motors took the place of steam engines. The first push-button automatic elevators started appearing in the 1920s, making elevator operators obsolete.
There was a surprising amount of skepticism about operatorless elevators. People did not want to run them themselves. They viewed this as too complicated, which Sounds very strange to us because they look the same. Many elevators had buttons very similar to...
Today's elevators are a far cry from the slow, moving rooms of the past.
Elevatoring is probably the most important thing for a very tall building. If you don't get the people up there, you don't have a building.
Builders of the new Taipei 101 in Taiwan faced greater challenges than normal when designing the ultra-sophisticated elevator systems for the world's tallest building. In a structure this large, just getting people in, out, up, and down presents unique challenges.
这栋楼完成以后，将会有12000人在这里办公。
There will be 12,000 people working in the building after it's completed. We know it's important to transport these people to the floor they intend to go to in a short time. Therefore, we divided the vertical transportation system into 3 zones in order to make transportation go more smoothly. Also, the elevators are double-deck elevators. This doubled the efficiency of vertical transportation.
The Taipei 101 utilizes 61 elevators. The larger double-decker elevators can carry 62 people at a time.
同时我们有最快的这个2部。
We also have 2 of the world's fastest elevators. The speed of the elevator is 1,010 meters per minute, or 60 kilometers per hour. It only takes 39 seconds to bring people up to the 89th floor.
At 37 miles per hour, the express elevators are the world's fastest. They're also the world's most advanced. The cars are streamlined to cut down on aerodynamic drag and wind noise. Toshiba Elevators of Japan spent more than a year testing various systems.
First of all, we must have a very powerful motor. Secondly, we need a little damper in the cab so that it will not move around too much.
Under each cab is a vibration balancing system, which uses sensors to quickly move weight back and forth to counteract vibrational forces.
And thirdly, we need to pressurize or depressurize the cabin in order to give people a more comfortable feeling on their ears.
Pressure chamber testing helped determine what was comfortable. The 2 express elevators move so fast, they're pressurized on ascent and depressurized on descent. To avoid a sudden change in atmospheric pressure, each cab has a high-pressure blower and exhaust release control system. Engineers on the Taipei 101 have pushed elevator technology into the stratosphere. Back in Los Angeles, the elevator mechanics are making good progress on the Caltrans building's 19 elevators. After 4 months, the first 2 are already up and running. They make Bobby's rig obsolete.
It's last week, Friday, right?
Yeah. Are you gonna miss me?
Oh, yeah. Everybody's gonna miss you out here, Bobby.
This guy's worked with me since back 20 years ago. He come in the elevator and said, hey, what?
After 42 years in construction and 25 years as a man-lift operator, Bobby's retiring.
Friday will be my last day, January the 16th. 42 years. It's all been good. I've helped put a lot of buildings up. I've brought a lot of cheer and made a lot of guys feel good about themselves. And it's been great. I'm gonna miss everybody. They all been like my second family.
Bobby, where you at?
I'm inside the elevator, having my ups and downs at Caltrans headquarters building. Okay, I'll get you on the rebound again.
Got a man in the shaded last week here, huh?
I'm gonna talk to the boss, see if I can get you, after I leave Friday, I'm gonna see if I can get you guys 2 days off.
13.
Hey, we appreciate that.
Saturday and Sunday.
When designing a building, Engineers and architects spend a lot of time creating a human environment that is both comfortable and convenient. And that includes creating a safe environment. One way engineers protect the structure of a building is to apply fireproofing to the steel skeleton. On the Caltrans building, fireproofers spray a coat of Monocoat MK6 on the exposed columns. It's a gypsum-based cement-like material that goes on wet and dries to form a hard shell. In the event of a fire, the fireproofing material will help insulate the steel from heat.
A fire in a building can easily reach 2,000 degrees. Structural steel starts to lose its strength around 1,000 degrees, and therefore steel isn't actually any more fireproof than, let's say, wood structure is.
Fires have been the bane of civilization for centuries. Fires spread easily between buildings, which were densely constructed, and most often made of combustible material, such as wood. American cities were no exception.
People were very concerned about fire in the 19th century because they had the experience on more than one occasion of major cities burning down. We don't have that today, but they had the Chicago fire. New York burned twice in the 1830s and again in the 1840s. Boston had a major fire. Baltimore had a major fire.
As early as the late 18th century, architects had begun the quest for what they hoped would be a fireproof building.
That's the first time we see builders trying to construct buildings without using any combustible materials. And that's what fireproof meant. It meant buildings constructed without using any combustible materials.
Unfortunately, the Great Chicago Fire of 1871 showed that merely using non-combustible materials, such as masonry or cast iron and steel, still left buildings vulnerable.
When it was discovered that the structural metal buckled or was damaged by high heat, the idea that it too had to be insulated from the heat led to the introduction of materials to protect structural metal.
Builders started encasing columns in terracotta, fired clay, to protect the structural members from heat during a fire. Later, engineers slathered plaster or concrete over wire to protect structural iron and steel members. When properly designed and implemented, these early fireproofing methods worked well. It wasn't until the 1950s that the first spray-applied fireproofing was introduced. But one of the ingredients of the early spray-on fireproofing posed a hidden danger: asbestos. Asbestos is a mineral which was used extensively in many products because of its fire-resistant qualities.
It turned out that the asbestos versions of spray-on adhered to the steel very well. And asbestos is a known fireproof material, which is why so much of the early fireproofing is laden with asbestos, because it was, in the 1950s, the best material they had, and they didn't yet know about the medical problems with it.
Studies showed long-term exposure to asbestos increased the risks of lung cancer. In 1973, the spraying of asbestos-containing material was banned. And therefore, the fireproofing we're spraying on the Caltrans building doesn't contain any asbestos. Fireproofing is meant to protect the structure during a fire, and as a result, save lives. But occupant safety hasn't always been the primary concern. Over the past 140 years, the emphasis on the protection of property during a fire has shifted to an interest in the preservation of life.
In the 1860s, when some kind of supplementary egress was first required in New York, most inventors came up with these block and tackle things that people were supposed to lower themselves out of their windows, or chutes. So there are just dozens and dozens of patents for totally weird and ridiculous things.
External fire escapes first appeared on tall tenement buildings and factories with heavy concentrations of people inside. But one horrific fire proved how inadequate the flimsy, poorly maintained, and rarely used outside fire escapes were. the most deadly factory fire in New York history occurred at the 10-story Ash Building in Greenwich Village on March 25, 1911. Hundreds of people, mostly immigrant women, were at work at the Triangle Shirtwaist Company, making clothing, when a fire broke out.
There were so many combustible things in that building. It was probably like an explosion. It spread very quickly. People could not get out from the stairways.
With the internal staircases blocked, some women tried the one external fire escape, but it collapsed under their weight. The fire department's ladders could only reach to the 6th floor. Although the fire lasted less than 30 minutes, 146 people perished, causing public outrage. Aftermath photos showed the human devastation. But they also showed just how well the building, which used fireproof construction, fared.
The structure of the building was able to withstand the heat of the fire. The terracotta fireproofing worked just fine. One of the reasons that people were so angry afterwards, they said, you know, look at all the effort that's been spent to save the building, but there was relatively little effort spent to save all these people.
The horrific fire sparked changes in health and safety legislation, including factory fire codes and labor laws. Today, a building's life safety systems are as important as any facet of design. Computers can help engineers design ever more efficient life safety systems.
It's called Fire Dynamics Simulator, actually. It was developed by the U.S. government for modeling these fire scenarios. It lets you build a building and then put a fire in, put systems in like sprinklers or smoke control, and then basically model what will happen during an emergency event and see where the smoke will go, what the temperatures will be like.
The life safety systems on the Caltrans building include 7,500 sprinkler heads, fed by 21 miles of pipe.
It's not like the movies where you see one goes off and sort of everything in the building starts getting flooded. Most sprinkler systems activate based on heat, so that the sprinkler that actually heats up will then fuse and activate, while all the sprinklers that are further away, if they're not heated, won't be pouring water down.
But the sprinkler system isn't the only emergency system. There are also 2 active smoke control systems.
Behind us there's some stairwell pressurization, which is basically a safety in case there's a fire. Pressurizes the stairwell, keeps the stairwell locked tight so there's no smoke can get in it when people are evacuating the building.
Another system inhibits smoke movement between floors. When smoke is detected on one floor, that floor becomes negatively pressurized relative to adjacent floors. In essence, creating a pressure sandwich that isolates the smoke and heat on the fire floor. Life safety engineers hope their systems never have to be used. But by applying the lessons of the past and implementing today's technology, they're helping ensure there is a tomorrow for those stuck in a building during an emergency. One of the most sophisticated systems in any large building is the heating, ventilation, and air conditioning, or HVAC system. Keeping the 750,000 square foot Caltrans office building cool in sunny Southern California is going to be quite a chore, requiring thousands of tons of equipment and 20 miles of ductwork.
Comfort is incredibly important because when people are not comfortable, when they are in an uncomfortable environment, people are less productive.
Arup is the mechanical engineering company on the Caltrans project. They're responsible for designing the systems that keep people comfortable.
Yeah, comfort's a combination of things: temperature, relative humidity, and air quality itself. These are the key components of comfort through the eyes of the mechanical building engineer.
Like every other party involved with the design of the building, mechanical engineers rely on computer software.
It's a computer-aided drafting tool, two-dimensional. What we start with here is a typical building layout. Here is the ductwork, the air conditioning ductwork layer, and on top of that we can start to add the lights, sprinkler heads, those sorts of things.
For complex systems, the mechanical engineer sometimes builds a 3D model to better visualize the way all the components work together. These tools are helping mechanical engineers design even more efficient systems.
We have taken the idea of indoor environmental control from a concept that once was considered the realm of the gods, something that was considered impossible to do, to the point now where it has become so reliable and so quiet, so inexpensive, and so hidden that most people think heating and ventilating and air conditioning is nothing more than a thermostat on a wall.
Before the 20th century, climate control was just a dream. For thousands of years, the only product people had to keep them cool was ice. But ice was primarily a seasonal luxury. However, by the 19th century, American entrepreneurs started harvesting ice in the winter and storing it in insulated ice houses for consumption in the summer. An iceman delivered the cold commodity door to door. But the ice was used in ice boxes for food preservation, not for room cooling. It took the hot lead from an assassin's gun to inspire one of the first attempts at an air conditioning system. In July of 1881, Charles Guiteau shot President James Garfield.
He was shot at the railroad depot in Washington, but lingered on for weeks after that. This was August, and Washington is a notoriously hot and humid place in August. In his doctor's judgment, this was having a negative effect on any chance of him improving, and certainly they wanted to make him as comfortable as possible.
Engineers from the Navy Department decided to adapt a recent invention for keeping food cold. Their device had a cistern filled with water and shaved ice. Ice water trickled down through a perforated metal pipe onto 36 terry cloth-wrapped rollers. A fan at one end blew air over the saturated rollers, then through ducts and into the president's room. At the same time, engineers tried to reduce the humidity by placing a large box filled with ice on the outflow side. Engineers believed the water vapor would condense out of the air because cold air can't hold as much moisture as warm air.
They called it air cooling, but in effect, they were hitting on exactly what it is that makes for modern air conditioning, and that is control of both humidity and temperature at the same time.
For 11 weeks, the device helped to comfort Garfield, but it wasn't enough to save him. He passed away September 19th, 1881.
The problem is it required 4 tons of ice a day to operate, just a prohibitive amount, even for the White House.
It wasn't until the turn of the 20th century that air conditioning as we know it was born.
Willis Carrier was asked as an employee of the Buffalo Forge Company to design a system which would control the humidity in the summertime at a printing plant so that the colors would properly register. What he did was to come up with a system which used a combination of cold well water as well as a mechanical refrigeration system to cool the water and then to dehumidify the air. That system that Willis Carrier developed started him on a journey which led to his ultimately being called by many people the father of air conditioning.
In 1904, Carrier applied for a patent for his apparatus for treating air. His device both cooled the air and controlled the humidity. His subsequent work formed the basis for air conditioning that is still used today. Movie theaters were among the first large structures to adopt the new technology. However, the expense discouraged new office buildings from quickly following suit. One of the first high-rises to employ air conditioning was the 38-story Philadelphia Savings Fund Society, or PSFS building.
Howe and Lescaz in Philadelphia in 1932 designed the PSFS building, which is the first modern, fully air-conditioned structure. Air conditioning continues to develop, but it's that moment when the tall building is free to be completely sealed up.
Beyond not having operable windows, the PSFS building had dropped ceilings to conceal ductwork. It had mechanical rooms on several floors to reduce the space required for vertical ducts. Engineers even hid the building's unsightly cooling equipment behind the distinctive PSFS sign on the roof. Even the Empire State Building, constructed just a couple of years before the PSFS building, didn't have air conditioning until 1950. The pioneering techniques first employed by the PSFS building are still being used today. The buildings constructed after World War II presented even greater challenges for climate control engineers. The tremendous use of glass as a popular cladding made keeping interiors cool more difficult. Fortunately, the development of more efficient HVAC systems, tinted glass, and window coatings ensured occupants wouldn't bake inside the glass-encapsulated buildings. At our building in Los Angeles, the first truckload of air conditioning equipment has arrived. The building's about to get a whole lot cooler. At our Caltrans building, the Scott Company is the mechanical contractor responsible for installing the systems the mechanical engineer has designed. To cool the building, Scott Company will install 3 massive carrier chillers, the largest being 30,000 pounds.
This is the mechanical room. This is where, in my opinion, the heart of this building lies. These are chillers which, if you were to think about it, are giant air conditioners. All of the cooling abilities of this building basically come from these 3 units right here. The water is pumped into these chillers, is cooled, forced out to different areas of this building to keep its occupants cool.
This process chills water to 44 degrees. The chilled water is then pumped to air handlers.
This is the air handling unit. Basically what happens is the cooled water from the chillers or the heated water from the boilers comes into these connections. And over here we have a coil. The water runs into this, through this coil, through these loops in this coil, whether it be hot water or cold water. And the air, which comes from this span over here, after it is drawn from a series of filters, comes over this way, goes over this coil, and the air is either heated or cooled and goes through the building to provide either cold air or warm air for comfort. The ductwork routes the air and takes it to where it needs to go.
This is actually the biggest job I've ever run. It's a real big job, and a lot of guys really don't think I should be running a job because of how young I am. I'm only 30. All eyes are on me right now. This job will either make me or it'll break me, and hopefully it makes me.
The 3 massive chillers that will cool the structure will also generate a tremendous amount of heat as a byproduct. So Scott Company is installing 4 cooling towers on the roof to take heat away from the chillers. Water circulates around a chiller to draw heat out of the machine. This condenser water, which is now hot, is pumped via 18-inch pipes to equipment on the roof.
Okay, what I'm working on now is condenser water piping. So, well, one of these 18-inch pipes is about 90 minutes each. They're visually inspected by a state inspector, and they can also be x-rayed if it's deemed necessary.
Basically what we have here is the fan section of the cooling tower, or the top section. The water comes in here on this PVC and is distributed amongst these nozzles. The nozzles spray the water out in a light pattern.
A fan pulls air up through the saturated baffles, cooling the water. But creating a comfortable environment is about more than heating and cooling. The V in HVAC stands for ventilation.
Ventilation is a very important aspect of the design of mechanical systems. Ventilation is the process through which you intentionally bring in air from the outside in order to remove or displace the pollutants that exist within a building. Pollutants like carbon dioxide and ozone and formaldehyde and other substances like that.
The air handler units bring in fresh air and mix it with return air from the building. Ductwork then carries the conditioned air into the offices. So we finally outfitted this empty shell with elevators, cooling equipment.
We don't belong here. Just throw the shit out. Look at all that stuff. All right. Just throw it out.
And hot tempers. The complex labyrinth of shafts, pipes, and ducts connecting every sector of the building like a giant web is representative of the diversity of experts it takes to create a safe, convenient, and comfortable human environment. And one of those experts who helped get this building up is retiring today.
Good day there. Enjoy your ups and downs with all the guys. Take care of them. Take care of the car.
Bye, Bobby. Good luck.
See you later.
It's a fundamental belief of ours that great buildings are made out of the unselfish collaboration of all the different parts.
Watching the building go from the ground all the way to the top and meeting a bunch of good people on it, looking back, you know, to be able to tell my family, hey, you see that big tall building? Your dad worked on it. And it's exciting.
From now on, the Caltrans building will have to manage its own ups and downs.
She's elegant, Miss Julie.
Δεσποινής Τζούλια.
I, the mistress of the house, honor the workers with my presence.
Το διάσημο θεατρικό έργο του Strindberg.
She thinks she can control everyone.
Στην πιο πρόσφατη κινηματογραφική εκδοχή του.
Dance with me again.
I'm at your service.
Don't be afraid, Kathleen. I won't run away with your fiancé.
Μια ιστορία αποπλάνησης.
My. I think you're shaking.
Και εξουσίας.
Now kiss my shoe.
I can't do that.
And if I order you to do it?
Colin Farrell. Jessica Chastain.
Excellent.
Δεσποινής Τζούλια.
You're playing with fire.
Are you ordering me now?
Yes. For once and for your own sake.
Παρασκευή 10 και 10 το βράδυ στην Ερτένα.
Ανακαλύψτε μας στο esismed.eu.
What does it take to get the lifeblood of a building flowing? Try 50 miles of pipe. Enough wire to stretch from New York City to Washington, D.C. 600 toilets. And a heck of a lot of solder. We'll find out how they used to do things. And we'll see through the structure we're building how these guys work today. Getting into the flow of things, getting wired, and getting plastered. So grab a seat. This show promises to be electrifying. Now, building a skyscraper, the arteries, on Modern Marvels. Pouring, installing, testing, sweating, and swearing.
Put number 2 right here.
In an effort to make this massive 750,000 square foot office building a reality. Building and making office life possible.
In the industry, we say that heating and cooling is a luxury, but plumbing is essential.
That will finally bring this structure to life.
Without water and drainage, society doesn't exist as we know it. Disease, everything that's been pestilence on man.
If anyone is, this job could spiral out of control.
Basically, plumbing system consists of two components. The pressurized water system delivering water to your fixtures, and the drainage system which takes the wastewater away. In installing a plumbing system in a building this size, we install the risers going from floor to floor.
Risers are the vertical pipes that move supply water up and wastewater down throughout the building.
In case of multiple bathrooms, we prefabricate whole batteries of toilets, urinals, whatever, particularly if they're repetitive multiple times. We bring out a package with the waste and the water already assembled and attached to the risers. This makes it fast and efficient, and then hook it up, test it, have it inspected, and it's done. That's it.
This is going to be a bathroom upon completion. We have the wall that's open with all the pipes in it now. We have the 2-inch water line here that will be furnishing the water to the water closets, toilets, and sinks. And this is the hot water line that will be furnishing hot water to the sinks. And then eventually there'll be a toilet sitting right here. That's the waste in the floor for the toilet.
The Scott Company is installing 700 toilets and urinals and 450 faucets. It's also running 50 miles of pipe, ranging from half-inch faucet supply lines to massive 12-inch storm drain lines. The plumbing engineer has to take into consideration many factors when designing a plumbing system. He starts by looking at the number of fixtures required by the building plans. Next, he determines how much water demand it takes to feed all the fixtures, in gallons per minute.
Without pressure, the water doesn't flow. The water flows totally under pressure to get it from one place to the other.
In all tall buildings, the city water pressure alone isn't enough to push it to upper floors.
Our supply is from the city. On this particular building, we go up 7 floors on city pressure, and for the upper 8th through 13th floor, it requires a pumping system.
Here we have the house pumps. These are pumps appear to be very small, but they do a very good job for the water servicing the whole entire building, all floors, all your lavatories, sinks, drinking fountains, your kitchen area. All the water that enters the building all goes through these pumps.
Each of these pumps is capable of moving about 50 gallons of water per minute. And this building will need that kind of volume.
A large building like the Caltrans building, for example, might use 15 million gallons of water a year. It would equate to filling a large NFL football stadium up to the stands with water.
That is a lot of bathroom breaks. But 15 million gallons is half of what a building this size could consume. Low-flow toilets and automatic faucets will help keep the state of California from flushing resources down the drain.
What's special about these is that they have sensors so that when you wash your hands, you take your hand away and the water stops running. It's going to save considerable in the long run.
In semi-arid Los Angeles, water conservation is a primary concern for the designers of the Caltrans project. This and other structures being built throughout the world are leaning more and more towards sustainable or green construction.
Our energy crisis in the United States, for a lot of countries around the world, is a water crisis. And green buildings offer a tremendous amount of attention towards water savings.
Making the biggest splash yet in the world of water conservation will be the 54-story One Bryant Park building, going up in New York City. Designers hope it will be the biggest, greenest skyscraper ever constructed. Developed by the Durst Organization and designed by Cook plus Fox architects, the building will use what's known as a gray water system.
The site is 2 acres in area, and each year, on average, 4 feet of water fall on this site. We're going to capture all of it, and we're going to use it to flush the toilets and for cooling tower makeup. And we're going to treat it before we use it.
The captured rainwater will be used in the toilets, but not in the urinals. The urinals won't use any water at all.
A waterless urinal looks just like any other urinal, except there's no flush valve on it. And it has a cartridge that is filled with a liquid that is lighter than urine. So when one urinates into the urinal, the water flows down the sides like any other urinal and actually flows under the liquid. It's a blue-colored liquid, harmless to the environment, flows under this liquid and right down the trap, down into the sewer system. And that liquid maintains the barrier between the sewer system and your nose.
One day we just sat down and did the math, and at 2 million square feet, if you look at the population and look at the number of times a urinal is typically flushed, it ends up being about 3 million gallons a year of water, potable water saved.
Although the urinals at the Caltrans building aren't waterless, they only use 1 gallon per flush. Most home toilets use 3.5 gallons per use. It's estimated the 2,000 occupants of the Caltrans building will flush 10,000 gallons of water a day.
That goes green means go.
The plumbing contractor is working to keep things flowing. But something doesn't quite smell right. And it's not coming from the sewer connect. The people working for the Scott Company are about to be hit with some really bad news. The development of the skyscraper is the story of technologies coalescing at just the right time to send structures soaring skyward. Technologies including indoor plumbing.
Public water supply is one of these great technological accomplishments of the 19th century. Without these water supply systems, you could not have the concentrations of population that you have in the cities and in those little cities that are skyscrapers.
Indoor plumbing in the U.S. actually predates the birth of the skyscraper. In 1829, the Tremont House in Boston became the first hotel in America with indoor plumbing.
This was considered an enormous luxury at that moment. But of course, once indoor plumbing was incorporated, it became a standard. And when we see plumbing coming indoors at the Tremont, we see plumbing coming indoors to stay.
By the time the first skyscrapers were constructed in the late 1880s, indoor plumbing had already become a common fixture of city life. But plumbing in a skyscraper presented unique challenges for engineers.
The story of plumbing in skyscrapers is really the story of the development of pumps. Pumps that were powerful enough to push water higher and higher in buildings that grew taller and taller.
With the help of pumps, designers found they could more efficiently control water demand and pressure by filling holding tanks at the tops of their buildings and letting gravity do the work. But the early office bathrooms weren't for everybody.
The early skyscrapers had single bathrooms at the core, and people walked down the hall to use the bathroom on every floor. Sometimes there was a men's room on one floor and a women's room on another floor. Sometimes in the early skyscrapers there were just men's rooms because there weren't very many women in office buildings.
Fortunately, the Caltrans building will have both men's and women's rooms. The Scott Company is outfitting 52 bathrooms with all the necessary items. But rumors have been swirling around the site.
A couple months into the job, found out that there's going to be some financial hardships. There was a crunch for money.
Worse than a crunch. The Scott Company, in business since 1906, became unable to pay its bills. Suppliers stopped providing equipment. That meant trouble for Clark Construction, the general contractor. The Scott Company handled not only the plumbing, but also the heating and air conditioning systems.
It impacted their performance dramatically. They were unable to keep up with the schedule here on this project.
But the schedule wasn't the only thing impacted by the cash flow problems. When union payments fell delinquent, a number of workers had to leave the job.
Worked for about 2 months, and company started to go belly up, and because we're organized through a union, we had to walk off the job. You know, for a lot of guys, it got real tough and real hard. Some guys like myself, I almost lost my house.
The trouble started in 2002, when the Scott Company worked on a Las Vegas super hotel, and the hotel skipped out on its bill.
A lot of the money, from what I understand, was being tied up on other jobs. They were owed a lot of money.
Reportedly, millions. The Scott Company started running out of materials, time, and personnel.
Why isn't he working? He should be started over there. He needs more manpower. The truth comes out. He needs more. Why does he get...
Once the rumors got out, naturally, a lot of people start looking for other avenues for steady employment. When you lose key personnel, it's hard to recover.
This floor looks clean. The only good thing about it, it's clean, but there's no work going on, right?
Clark Construction stepped in to try to retain crucial people. Clark even paid suppliers directly, just to keep the job going. But Clark couldn't keep the Scott Company going. After a century of service, the Scott Company was forced to close its doors. Fortunately for the project, Clark Construction was insured for events like this.
And we'll be able to get to that shortly.
The build team chose Western Air as the replacement plumbing contractor, and the transition went smoothly. Western Air even hired many former Scott employees who knew the project, including Ed, plumbing foreman, Steve, general foreman, and Joe, piping superintendent.
I'm going to finish this job up. Western Air has talked to me a little bit about staying on with them, and like I say, they seem to be a very, very good company, and I will probably stay on with them if the occasion arises.
As Clark struggles to keep everything on schedule, they're hoping there are no more shocking surprises, especially since the electricians are in next to get this building wired. Plug it in, flip a switch, light it up, turn it on, and crank it up. Electricity keeps our big buildings running. Broken down, it's somewhat similar to the electrical system in your house. At home, power travels from the panel board to the outlet through the hot wire. When you're using a power tool, such as a drill, electricity flows through the hot wire, powering the drill, then back to the panel board via the neutral wire to complete the circuit. The ground wire is there to provide a safe path for electricity to follow in the event of a short circuit, which might result from a loose hot wire in the drill. The electrical system of this building follows the same basic rules, but on a much bigger scale. It starts 4 stories below ground in the electrical vault.
The vault is owned by the Department of Water and Power. The contractor actually built the vault for us to our specifications, but it's our equipment, our facility, and we're responsible for it. So only the Department of Water and Power has access to the vault for safety reasons and also because it's our equipment.
Chris Logie with the Los Angeles DWP is in charge of setting up the vault. It's the first step toward getting this building turned on.
We're installing the equipment, the transformers, the fuse cabinets, and we're just starting from scratch. It's certainly my biggest project to date. This is a big, big job.
The fun begins as the first truckload of equipment arrives at the site.
Pipes that are running underground, and they're all over the city, and they're bringing in a very high voltage cable. It's 34,500 volts. That voltage is brought in, and it's brought into these large transformers. And what the transformers do, imagine the word transformer, it transforms that high voltage of 34,000 volts into something that people can actually use, 480 volts.
With every electrical system, especially one this massive, there are safeties built into the system. This system has multiple safeties, including breakers and fuses.
Each transformer has got a fuse cabinet. You might be able to see them behind me. They're about 11 feet tall, giant fuse cabinets. At home, the circuit breaker panels, they're there to protect the wire in your home from overheating. You happen to put too many pieces of equipment on, like a toaster and a microwave. Well, the fuses in this room are here to protect the transformers. If there's too much of current drawn, before the equipment can be damaged, the fuse blows.
What we use it for is a safety measure, so that in case something goes wrong, the electricity will follow this to ground, which we have it hooked to. We have it hooked to a ground system under the floor. It's just like the wire you have at your home, except probably it's only one strand of this.
Electricians take over where the DWP workers leave off, installing the rest of the equipment, conduit, wiring, and lighting.
Well, we're out of the vault. Now we're in the main electrical room that the vault feeds. This is one of our switch gears. In layman's terms, this is kind of like a big breaker box. It has several different breakers, and each breaker has a different function. One might be turning on the air conditioning equipment, one might be turning on the elevators, and so on and so forth. This is just one breaker right here. That's practically the size of a washing machine as compared to the size that you're used to turn on and off with your fingers in your house.
From here, electricity travels up to electric rooms on each floor.
We're on the 7th floor. This is the south end, the electric room. So from downstairs where the main electric room is, we have some of this bus duct risers, which is large pieces of copper busing that come up through the building, carries a lot of power, more than wire could. And we stick a switch here to grab onto it. It's got a circuit breaker, big wire. And what that does is it feeds this transformer, which will take it down to a voltage that's more usable in the building. From there, it goes to the distribution board. From here, it goes up, it goes down. It happens to also feed these 3 branch circuit panels on the 7th floor, which from here go out to all the office space to feed their receptacles and their lights and plug their computers in.
Wires transport the juice from the panel board to the receptacles. Electricians run metal-clad or rigid metal conduit to protect the wires from getting damaged in the process of installation, or being nicked by a rogue nail driven into the wall to support a picture frame. To get the wires into the conduit, the electrician inserts a flexible wire tool. When it reaches the other end, it's connected to the electrical wires and pulled back through the conduit. Each one of these 50,000 electrical wires has an exact place it needs to go. That's why they need a good roadmap.
How about electric here? Where is this fed from? Can you start looking at Amos where these things are fed from?
With 6 months to go before the first scheduled move-in date, the subcontractors are feeling more pressure than ever to get this building switched on.
Hey, it works.
And there's one man in particular applying the pressure. Clive Sondy, the general contractor.
So how long is it going to take to finish this? There's the plumber doing the work. How long, Sonny boy? Tomorrow you'll be done.
Oh, hopefully.
Yeah.
Hopefully.
Okay, good deal.
Okay, you're all right. I don't care what they put.
The 85 electricians at the new Caltrans building in Los Angeles are busy installing the transformers. running conduit, and pulling wire. They're also hooking up 6,000 fluorescent lighting units. The modular design makes each one a snap to install in just a few minutes. Proper lighting has always been essential to productivity. Until the early part of the 20th century, lighting, natural lighting, influenced the very design of the building itself.
Workspaces were lit principally by daylight, so that the close proximity to windows was extremely important for the quality of space.
At the turn of the 20th century, Chicago architects designed central courtyards that allowed light into the center of the structure. In New York, architects designed tall, slender towers. Appearing in both cities were buildings with indentations for better access to light.
And it was the incandescent electric bulb, Edison, 1879, that changed everything. And it was during the 1880s that electric lighting began to come into use on a commercial basis.
Edison didn't actually invent the light bulb. He invented a less expensive, longer-lasting, and more reliable light bulb. He also patented switches, outlets, and sockets to support his light.
Thomas Edison realized the light bulb needed electricity, and there was not any power generating plants at that time. So while he had a great invention, there was nothing to plug it into.
On September 4th, 1882, Edison's Pearl Street plant opened in Lower Manhattan, becoming the country's first commercial electrical generating station. Built in the heart of New York's financial district, the plant initially provided electricity for lighting to 59 customers in a 1 square mile area. Just 2 decades later, large buildings throughout the country were using electricity to run lights and elevators. The early electric lights were more for task lighting than room illumination. But the shape of things started to change with the introduction of fluorescent lighting in the late 1930s.
After the invention of fluorescent light, the internal space of the office could be much deeper than it was before because fluorescent lights are cool. So you didn't need to have any longer the light wells that cut into the space.
While the electrical engineering company on the Caltrans project isn't facing the same challenges Edison faced, the obstacles are still daunting. Today, owners aren't satisfied with electrical systems that merely function. They also want them to be efficient. No one wants to get shocked by an electric bill. It's estimated that 1/3 of all the energy used in the U.S. is consumed by large buildings.
Our aim is to try to reduce the amount of energy that it takes to support the building.
Arup, the electrical engineer, working with the architect, has come up with some bright ideas to help conserve power in the Caltrans building.
We do that by designing a more efficient mechanical system by using light fixtures which produce less heat, so there's less cooling.
Each light fixture has a motion detector, so it only turns on when it's needed. The sun also helps light the building.
The south side has photovoltaic cells, so they produce energy. If you use half of the amount of energy, you also spend half the amount of money every year. And if with big buildings, those are several $100,000 of savings every year.
The One Bryant Park building in Manhattan will have another cool way of saving money. Because electricity rates fluctuate throughout the day and night, power is more expensive during peak demand, usually midday. The One Bryant Park building will maximize its electricity usage through a system called off-peak cooling.
In Manhattan, we stress out the electrical infrastructure on very hot days in the middle of the summer all at the same time. And it's just incredibly inefficient. So one of the unique technologies that's happening here is called ice storage. In the middle of the night, when there's very little stress on the infrastructure, we're going to use chillers to make ice all night long, like a chipmunk storing nuts for the lean times. And then in the peak of the day, we actually have cold stored up.
Inside each large tank are dozens of spiral tubes, stacked on top of each other. The tanks are also filled with water. At night, coolant from the chillers is pumped through the tubes, freezing the water solid in the container. During the day, warm coolant is pumped back through the tubes, drawing cold from the ice and chilling the coolant. The chilled coolant then goes to air handling units to cool the air. Although off-peak cooling is already being used in many buildings throughout the world, the One Bryant Park building is several years from completion. The Caltrans building, on the other hand, is in the final stretch. Everyone is racing toward the finish line, and people are starting to sweat.
A lot of work in here. When you get a date out of these guys, I want to finish this crap. I want to get done.
It's been 22 months since excavation began. Clark Construction, the general contractor, is struggling to get the building finished.
Schedule is very important. We have a contract to deliver this project to the owner, and you have a set date. They expect to move into this building.
That date is August 13th, 2004, less than 4 months away. To add to the pressure, Clark faces penalties of $25,000 for every day it's late.
Great, great.
Over the past 21 months, Clark has faced rain delays, a distraught man hijacking their tower crane, mock-up testing trouble.
We got some water here. We got to find out where it's coming from.
Elevator ropes jumping off their shiv, and the bankruptcy of the project's plumbing contractor. While every job experiences road bumps, it's Clive Sondy's job to make sure no pothole turns into a bottomless pit.
Clive is the on-site superintendent. He's the one that's making sure that everybody's meeting their deadlines.
They must need a C&I dog or something. The ones upstairs are not done.
Clive is what you might call a motivator.
I don't know why this can't be done. Is there any reason this can't be done? Can you kick them in the ass and get them done? Well, you got to plan ahead and always come up with almost goals that people can't meet. Why isn't it up in the air? What the hell are we waiting for? Shoot for the moon, and if you get real close, you're in good shape.
He is very, very direct. He tends to be to the point.
Well, if there's no freaking problem, why isn't this done?
Which is good, because you don't want to beat around the bush.
We don't belong here. Just throw the shit out. Look at all that duck.
All right.
Just throw it out.
I'll talk to John
And charge him for it.
But he's pretty much a general out there.
I'm tired of babysitting. I'm not a babysitter.
Personality-wise, it's kind of like Lombardi. You hate him, but you respect him. And if a person in his position isn't constantly, I hate to say it, hated, then he'll probably get walked all over. I think he's doing a fantastic job.
In many ways, Clive is like a stern father, making sure his kids are getting their chores done. He's also looking out for their well-being.
You got safety glasses?
Yes, sir.
Okay. And that ladder say that you can't go on the last 2 steps? Almost every ladder I've ever seen, you're close to a shaft. I'd hate to see you go down. How you doing there, Sparky?
Pretty good.
When I'm building a rocket ship, it's mostly common sense and experience and knowing what things are supposed to look like.
Tight flange.
He's an old steel man. You guys should get along good.
Yeah.
Like any other business, you're only as good as the people you have. You got to treat them well. You got to train them well. And if you lead properly, they'll follow you.
In June 2004, Clive Sondy was diagnosed with cancer and had to leave the project abruptly. He underwent surgery 3 weeks later to remove a portion of his pancreas. Clive is currently recovering from the major surgery.
figure out how many phones they want, how many data locations they want. And then we come in and we start roughing in the cable, which is pulling the cable in. We pulled in 1.5 million feet of data cabling. We also pulled in about 20,000 feet of voice riser cabling. We keep track of all the wires by a really, really good labeling schematic. Everything is labeled. You can't forget any labels. You really can't.
While the cable is being roughed in, technicians on the second floor are outfitting the central computer and phone rooms with servers and voice equipment.
This here is the voice MDF, main distribution frame. Basically what happens here is SBC, the phone company, will bring in lines from the street and they will hand them off to us, the building. They're gonna bring in 3,600 lines.
The adjacent room holds the heart of the data network.
This is the data MDF, the data main distribution frame. What happens here is we've sent fiber optics throughout the whole building to all the IDFs, the independent distribution frames. We have 2,400 fiber lines. And what we're doing now is testing them to make sure they work. Every computer in this building will be talking through this room.
Fiber optics are long, thin strands of glass which use light signals to transmit information. Technicians use fiber optic cable because it can carry far more information over longer distances and at a much faster speed than traditional copper wire.
2 of these fibers, because you need a transmit and a receive, 2 of these fibers could probably run this whole building if they wanted to be on one network. Every computer in this building.
But there will be dozens of departments with individual networks and servers. The fiber optic cable travels up conduit to independent distribution frames, or closets, on each floor, where copper wire then takes the information to each phone and data jack.
The most important aspect of my job is to have the customer come in, to plug in and have no problems at all with their data.
But that goal might be hard to meet with less than a week before the first move-in. While Dave's struggling to get everyone wired, a few select Caltrans employees are getting a sneak preview of their new digs.
Man, have you made progress?
Well, I love the space. I just love the way the lighting's working for it.
While the excitement is growing for Caltrans, the anxiety is building for those racing to get the structure finished in time. Brian Day, project director with the California Department of General Services, has been here at the site as a liaison between various groups, including Caltrans, the end user, and Clark Construction, the general contractor.
Have they changed? Are they increased or are they staying constant?
This week is perhaps the most pressure-packed. We have people on site working 24/7. We have exactly 4 days left. We have 4 days left to complete the fire life safety testing.
Can't have that,
The Caltrans District 7 user group begins moving equipment and furniture over Friday, August 13th. And we anticipate meeting that date.
This is one of the final steps. If the state fire marshal sees anything not yet up to snuff, the Caltrans people can't move in at the end of this week. Considering the complexities of construction, it's amazing that a project stretching back 3 years could be mapped out so carefully that it might actually meet its completion deadline. Let's rewind a bit.
But when you see the skin and you look at the real one and you realize it has holes in it and it builds up color.
I never come up with an idea and that's the project and I hand it to you done. It's not the way it works. I see the creative process and architecture as something much more evolutionary.
We actually started excavation on April 23rd of this year. To date, we've moved about 190,000 out of 200,000 cubic yards of dirt.
There's a few different ways to place concrete. Shotcrete is where it's actually blown onto the wall with high air pressure.
The most difficult job is the steel erection itself, is actually putting the structure up. And the guys that have the most difficult job is the raising gang along with the 2 connectors.
It's a big day for any construction site. This is why we usually have these parties.
These are chillers, which, if you were to think about it, are giant air conditioners.
These are the strip window units we're installing out here. We have around 1,000 of these to put in.
Grab the number 1 right here, put number 2 right here, so I can get 1 and 2 in order here.
Without water and drainage, society doesn't exist.
We're on the 7th floor. This is the south end, the electric room.
Sure, we're connecting wires and we're connecting computers, but what we're really doing here is connecting people.
This project could have easily taken a 6-year envelope. We've basically cut that time envelope in half, from an existing asphalt parking lot to a 1.2 million square foot structure. Is truly an outstanding effort.
The Caltrans building was a fast-track project. To save time, construction began before many details were hammered out. This took the coordinated efforts of the architect, the general contractor, the subcontractors, the state, various engineers, and consultants. From a construction standpoint, the fast-track method proved successful on this project. But the real critics have yet to weigh in. The people taking over this building in just a few days.
One set of employee elevators.
I love this building. This is going to be great. The interior space is fantastic for the employees. We get lots of natural light all through all the workspaces, which is very important.
This is my first time being inside of the building, and I must say it's fantastic. And I know that employees will definitely enjoy working here.
As we've watched the building under construction, just from across the street, the anticipation has grown over time. It started with a big hole in the ground, and it slowly worked itself up. It'll feel vibrant and like part of Los Angeles, unlike we felt before.
Thousands of independent events have transpired to form a building. And like all large building projects before it, this one too takes its place in the skyline and in the fabric of the city itself. The planners, designers, and builders of this project are already looking ahead to their next undertaking, where they'll face new challenges in the race to build the next monument.